Every second, thousands of tons of pressurized water crash into hydroelectric dams across the globe. Converting that raw, chaotic momentum into stable electricity requires a highly specialized mechanical bottleneck. That bottleneck is the Francis turbine. It is the industry-standard mixed-flow reaction turbine, a machine specifically engineered to strip high-pressure fluid of its kinetic energy and translate it into continuous mechanical work. To see how it operates, we have to look inside the casing. This diagram shows the Francis turbine's mixed-flow path. Fluid enters radially, moving inward from the outer perimeter, and then drops, exiting axially straight down the center. The process begins in the spiral casing. This outer ring receives the incoming water and distributes it evenly around the entire circumference of the machine, ensuring the internal pressure remains balanced. From the casing, the fluid is forced inward through a series of stationary guide vanes. These direct the flow straight into the central rotating component, the runner, where the actual energy extraction takes place. High-efficiency energy conversion depends entirely on the precise mathematical geometry of these internal stators and rotors. This two-dimensional cross-section isolates the precise components responsible for manipulating that pressure. Looking at the spiral steel case on the edges, notice how the cross-sectional area gradually decreases. This reduction maintains a uniform fluid velocity as water is drawn closer to the center axis. Next, the flow hits the wicket gates, or guide vanes. These stationary blades act as nozzles. They accelerate the water and inject it into the runner at a highly specific, mathematically calculated entry angle. The runner is the active zone. Here, the fluid's kinetic energy and pressure physically transfer a massive turning moment to the vertical shaft before the water drops out into the draft tube below. Designing these runner blades requires translating raw fluid force into strict vector kinematics. The curves are calculated down to the fraction of a degree. Engineers map these fluid forces directly onto the curved geometry of the turbine blades using a framework called velocity triangles. This diagram shows the inlet tip velocity triangle. The vector labeled v1 represents the absolute velocity of the water jet, exactly as it leaves those stationary guide vanes. The angle alpha is the guide blade angle. It dictates the absolute trajectory of v1 relative to the tangent of the spinning wheel. But the blade itself is moving. u1 represents the tangential velocity of the metal blade. When we subtract the blade's motion from the water's absolute velocity, we get vr1, the relative velocity of the fluid as it physically slides across the metal. We can break the absolute velocity v1 down into two operational components. The vertical leg, vf1, is the flow velocity, the force pushing the water through the machine. The horizontal leg, vw1, is the whirl velocity, the actual rotational force being applied to the turbine. To capture this energy without causing destructive boundary layer turbulence, the water must enter smoothly. The physical angle of the metal runner vane, theta, must perfectly align with that relative velocity vector, vr1. We can calculate these required manufacturing angles for any given set of flow conditions. Looking at this calculation for the guide blade angle, alpha, we derive it from the tangent function, specifically taking the ratio of the incoming flow velocity over the whirl velocity. In this system, the math dictates an angle of exactly 13 degrees and 55.7 minutes. This number permanently sets the physical orientation of the stationary wicket gates during manufacturing. Next, we calculate the runner inlet angle, theta. Because the wheel is spinning, this equation must subtract the blade's velocity, u1, from the whirl velocity, vw1, in its denominator. The result is 41 degrees and 5.4 minutes. That is the exact metal curvature required to catch the incoming fluid stream without kinetic shock. Calculating these two angles correctly synchronizes the high-pressure output of the stationary casing with the rotating intake of the turbine wheel. As the water travels down the blade, the engineering goal is to extract the maximum possible kinetic energy before the fluid leaves the outlet tip. Reaction turbine optimization relies on a strict rule. Water must exit with zero swirl. This means the final whirl velocity, vw2, must equal exactly zero. When the whirl velocity is forced to zero, the absolute exit velocity, v2, becomes entirely axial. It aligns perfectly with the downward flow velocity, vf2. To lock in this optimized state, engineers first calculate the peripheral blade velocity at the smaller, lower diameter of the outlet, determining u2. Using that outlet velocity, we derive the final outlet vane angle, phi, by taking the ratio of the exit flow velocity to u2. By forcing the final whirl velocity to 0 through this calculated exit angle, we ensure every available joule of rotational energy has been successfully stripped from the fluid and sent into the main shaft. Once the water surrenders its energy to the runner, it enters the final phase of the flow path. Because of the massive energy extraction that just occurred, the water drops into the draft tube at a pressure significantly below normal atmospheric levels. The draft tube solves this. Its expanding conical geometry carefully decelerates the low-pressure flow, converting the remaining kinetic energy back into pressure, so the water can be safely discharged into the tail race. At this industrial scale, a deviation of even a few degrees in these calculated angles results in multi-megawatt losses of potential power output. The Francis turbine generates gigawatts of electricity by operating as a flawless mechanical translator. It proves that harnessing macro-scale power is an exercise in mastering microkinematic geometry.